Hello, my dear friends. Today I'm going to present you a study which examines a relatively simple but increasingly important question. Does the effectiveness of motivational mechanisms depend on the cognitive state of the user? More specifically, we compare two motivational approaches, gamified incentives and intrinsic motivation, and examine how their effects change when users operate under low versus high cognitive flow. Our central argument is that motivational mechanisms should not be considered universally effective. Their effectiveness depends on the cognitive resources available to the user. The issue is particularly relevant for contemporary digital and AI-driven environments where users increasingly interact with complex information, multiple stimuli, and time-constrained decision tasks. Digital environments increasingly use motivational mechanisms to improve engagement, performance, and decision quality. Gamification is one of the most widely adopted approaches. Points, badges, leaderboards, and similar mechanisms can make tasks more engaging and can encourage users to persist. However, the empirical evidence is not uniformly positive. One possible explanation is that gamification itself requires users to process additional information. When the digital environment becomes cognitively demanding, users have fewer cognitive resources available to respond to external reward structures. This leads to a central problem addressed in our study. We ask whether intrinsic motivation and gamified incentives remain equally effective when cognitive resources become constrained. The key research question is therefore how cognitive overload changes the relative effectiveness of these two motivational mechanisms. The study integrates two theoretical perspectives. The first is self-determination theory, which emphasizes the importance of autonomy, competence, and relatedness as foundations of intrinsic motivation. Intrinsic motivation is particularly relevant because it is associated with sustained engagement and deeper cognitive processing. The second perspective is cognitive load theory. According to this framework, working memory has limited capacity. When information demands, multitasking, or time pressure exceed this capacity, attention and information processing become less efficient. These two perspectives suggest an important interaction. External rewards may require additional cognitive processing and therefore become less effective under overload. Intrinsic motivation, in contrast, may be more internally regulated and therefore relatively more stable. This represents the main research gap addressed by our study. There is limited direct evidence comparing these motivational mechanisms under different levels of cognitive load. Our conceptual model proposes that both gamified intensive and intrinsic motivation influence engagement. Engagement is then expected to function as an important mechanism linking motivation to behavioral outcomes, specifically decision quality and behavioral intention. The critical variable in the model is cognitive overload. We conceptualize cognitive overload not simply as another predictor, but as a boundary condition that changes the strength of motivational relationships. Under low cognitive load, we expect gamified incentives to be effective because users have sufficient cognitive resources to process external reward structures. Under high cognitive load, however, we expect the effect of gamification to weaken. At the same time, intrinsic motivation is expected to remain comparatively stable. The six hypotheses summarize these relationships with a particular emphasis on the moderating role of cognitive overload. Methodology: the study combines a theory-driven stimulation with a controlled laboratory experiment. First, we generated a simulated dataset of 250 observations. The purpose of simulation was not to claim empirical representations of a population, but to test the proposed structural relationships under controlled conditions. Participants in the simulated framework were assigned to low or high cognitive low conditions, and the construct were operationalized using 5-point Likert type measures. Second, we conducted a laboratory experiment with 30 participants. They were divided into two groups, a gamified incentive condition and an intrinsic motivation support condition. Cognitive load was manipulated through information density and time pressure. The gamified condition used points, badges, and leaderboard feedback. The intrinsic motivation condition emphasized autonomy and informational feedback without external rewards. Finally, we applied regression, ANOVA, structural equation modeling, and robustness analysis. The SEM analysis used 5,000 bootstrap resamples, while Monte Carlo analysis included 1,000 iterations. Let me now turn to the main results. The regression analysis provides a clear pattern. Intrinsic motivation is the strongest predictor of engagement with a standardized beta of 0.49 and p below 0.001. Gamified incentives also have positive and statistically significant effect, but the effect is considerably weaker with a beta of 0.21. Importantly, cognitive overload has significant negative effect on engagement with a beta of minus 0.37. The second part of the analysis concerns decision quality. Here, engagement is the strongest predictor with a beta of 0.44. Intrinsic motivation also has a significant direct effect, while gamified incentives do not have a statistically significant direct effect on decision quality. This suggests that motivational mechanisms primarily influence decision outcomes through engagement, while intrinsic motivation also contributes directly to decision quality. The most important finding concerns the role of cognitive load as a boundary condition. Participants in low load condition report substantially higher engagement, 4.18 compared to 3.72 under high load. The same pattern appears for decision quality, which decreased from 4.02 to 3.54 when cognitive load increased. The experimental results provide additional support. Intrinsic motivation produced higher engagement than the gamified condition, with a statistically significant difference and strong effect size of Cohen at d equal to 0.84. Even more importantly, under high cognitive load, decision quality was significantly higher in the intrinsic motivation condition, 3.82 compared to 3.41. The effect size was large, with Cohen's d equal to 0.97. These findings support the central proposition of the study. The effectiveness of gamification decreases as cognitive demand increases, whereas intrinsic motivation remains comparatively robust. How can we interpret these findings theoretically and practically? One explanation is a cognitive bottleneck mechanism. When working memory is heavily loaded, users may have less capacity to process external reward signals such as points, badges, and leaderboard information. Intrinsic motivation may be less dependent on this external information or cues because it is more closely connected to internalized needs such as autonomy and competence. It may remain more stable under cognitive strain. This leads to an important implication for AI-driven systems. Motivational design should not necessarily be static. Instead, cognitive load could be treated as a real-time state variable. An adaptive system could estimate the user's cognitive state and dynamically select the appropriate motivational mechanism. For example, under relatively low cognitive load, gamified incentives could be introduced to increase salience and engagement. Under high cognitive load, the system could reduce external stimulation and instead emphasize autonomy, meaningful feedback, and competence support. In this way, the system becomes not only personalized but also cognitive state aware. To conclude, our study demonstrates that motivational effectiveness is not universal. Gamified intensives can enhance engagement, particularly while cognitive demands are relatively low. However, their effectiveness decreases under cognitive overload. Intrinsic motivation shows a more stable pattern and becomes particularly important when users face complex and cognitively demanding tasks. Engagement emerges as a central mechanism connecting motivational factors with decision quality and behavioral intention. The main theoretical contribution is therefore the identification of cognitive overload as a boundary condition that changes the relative effectiveness of extrinsic and intrinsic motivation. From an applied perspective, the findings suggest a shift from static gamification toward adaptive motivational design. Future research should move toward real-time AI systems capable of detecting cognitive flows through behavioral and psychological data and dynamically adjusting motivational interventions. A key limitation is the relatively small experimental sample, so larger empirical studies are necessary to establish broader generalizability. Ultimately, our proposition is that intelligent digital environments should not simply ask how can we motivate the user. They should ask a more precise question: how should we motivate this user given their current cognitive state? My dear friends, thank you for your listening, and now it's time for questions and answers. Thank you very much and have a very nice day.